live on YouTube.
Should we let the people get in, right?
Yeah, I think
Yeah,
I'll do that here. So, okay.
Do you want to be, I don't know. I'll do all of that. Okay, thank you.
Okay, so welcome everyone to today's seminar. Before I start, I would like to remind you all that this presentation will be recorded. You may post your questions to the chat session and we will take them up one by one at the end of the talk. So today we have Rick Chappell with us, who will be talking about the role of the Earth's ionosphere in populating the magnetosphere and driving its dynamics. Rick Chappell is a research professor of physics at Vanderbilt University and consults with NASA regarding solar terrestrial physics. Following his undergraduate work in physics at Vanderbilt and his PhD in space science at Rice University, he worked at the Lockheed Palo Alto Research Laboratory, where he used data from the OGO-5 satellite to study the creation and dynamics of the plasma sphere. Later, at the NASA Marshall Space Flight Center, he broadened his work on the ionosphere magnetosphere to include the contribution of the low-energy ionospheric polar wind outflow to the different energetic plasma regions of the magnetosphere. He was the principal investigator for low-energy ion instruments on the Dynamics Explorer and Polar satellites, and is currently involved in analyzing low-energy ion measurements from the Fast Plasma instrument on the MMS spacecraft. Welcome, Rick, and you may take over from here.
Okay. let's see, I think I need to bring this up. Okay. Okay, how does that look, everybody? Can
We
you-
don't see your slides yet.
You don't see them yet.
No.
Okay, all right. So I need to,
Yep, there you go.
so you can see them now.
Yeah, we can see your screen.
Well, for some reason, let's see, can I put this up? Can you see it there? Can you see it now, Reem?
Yeah, now you can go to the presentation mode, maybe.
Okay,
Okay, perfect.
well, all right, let's see here. Okay, great. Well, it's an honor for me to participate. I've been enjoying these seminars now throughout their lifetime and learning a whole lot. And it's a pleasure to share some information about how the Earth's ionosphere populates different regions of more energetic particles in the magnetosphere. And more recently, we're looking at how the ionosphere can drive the dynamics of the magnetosphere. This is just going to be a tutorial in the beginning, and then toward the end, I want to show you some new results that are basically continuing to build a case for the role of the ionosphere and important processes in the magnetosphere. I might say this is my half-century anniversary of working on this topic, and it's been a great journey to see how the perspective of the community has evolved in terms of the role of the ionosphere. We've always thought about the ionosphere as playing a very important role in storms and substorms as a recipient of energy from the magnetosphere and setting up the current systems that cause all of the storm dynamics to happen. We're going to look a little bit differently at that in this talk and ask the question, not how does the ionosphere respond to magnetospheric storms, but how does the ionosphere cause magnetospheric storms to happen as a driver. So I want to start with some history. Well, let's see here. For some reason, that's not working. So I'm not sure what my situation here. Can you hear me?
Yes, we can hear you.
You can hear me. So let's see. I'm sharing, but I'm unable to. My computer is not driving the slides, and it's not letting me get back into them either. So how do we, Jason, I may need some help on this.
Sure. Yeah, I wonder if you push the escape button on your computer, I wonder if it would take it out of the presentation mode or.
It's not. It's apparently not talking to it. Let's see.
Oh, there we go. It looks like it's working now.
Okay, let's see how that does. Okay, great. All right.
Yep.
So just objective wise, we want to talk about the influence of the ionospheric plasma throughout the magnetosphere. That is in regions like the plasmasphere, plasma trough, polar cap, magnetotail lobes, plasma sheet, warm plasma cloak, rain current, radiation belts. All of the major areas the ionosphere is playing a role. Initially, we want to show how the ionospheric plasma that has energies of only an EV or so can become energized in the magnetosphere to the energies of the different regions that it ends up in, actually helping create or dominatingly create many of those regions. We want to look at the trajectories that show how the cold ions are energized into the different regions that they move. and then in combination with the solar wind BZ, show how the ionospheric particles become a major driving mechanism for substorms and storms. And as a reminder that ionospheric ions, both from the plumes that come off the plasmasphere, the warm plasma cloak that brings particles to the nose of the magnetosphere, affects the reconnection process, both at the nose of the magnetosphere and in the tail. And then a reminder that these particles are very difficult to measure because of their low energies and the effect typically of positive spacecraft potential, which means that you don't see them often. And many of our early measurements of the magnetosphere had no measurements of anything in the lobes because the spacecraft was charged enough that it cold not see the cold plasma. Okay, let's see here. So historically, this is an image that was done many years ago, decades ago, that was initially done to show the solar wind entry into the magnetosphere and formation of the regions of the magnetosphere. The more we went along, this figure originally was missing two very important things. We did not know about the polar wind at that point, the very low energy outflowing ions. And we could not tell the difference between H plus ions that come from the solar wind and H plus ions that come from the ionosphere. To the measurements that we make, they look exactly the same. And so jumping ahead, we're going to have to model that with multi-fluid merged MHD models, which I'll mention something about. So those two things, the inability to even see this outflowing polar wind and the inability to tell the difference between solar wind and ionospheric H plus, left us with a thought that all of the magnetospheric plasmas, with the exception of the plasmasphere down inside, all of that came from the solar wind. Now, our historical measurements also led us to that inaccurate conclusion, because early on in missions, we could measure the very high energy particles, but not the low energy ones. So we flew Geiger counters on the early explorers and measured the radiation belts. And then with channel multipliers, we were able to measure energies down to 100 eV or so in particle detectors. And we started seeing the plasma sheet and the ring current. Some of the ion traps could measure the plasmasphere down to a few eV, but the spacecraft, particularly those who went farther out into the magnetosphere, had no spacecraft potential control, and so they couldn't see the low energy particles. So it led us to think the solar wind's probably delivering most of the populations to the magnetosphere, which we're now finding is not the case. So when I went to Lockheed, I worked in the auroral physics part of Lockheed, working with Dick Sharp and Dick Johnson, Ed Shelley, looking at auroral particle instruments. And then there was an opportunity to switch over within Lockheed. This is at the research lab in Palo Alto. Switch over and work on data from the Yogo 5 mission from the light-down mass spectrometer, which Jerry Sharp and Kent Harris and Bill Knudsen worked on. And Martin Walton was kind enough to give me a job after finishing my PhD and giving me a job to work in the great environment there in Palo Alto. But so I started working on the low energy particles, and in looking at the dynamics of the plasmasphere, what we realized we needed to measure the low energy particles more carefully with instruments with larger geometric factors and spinning, so we could get pitch angle distributions and as well as composition and energies to see where the ions were moving how they were moving out of the ionosphere into the plasmasphere. And so we proposed an instrument for Dynamics Explorer, the retarding ion mass spectrometer. Dynamics Explorer was two spacecraft, one down low and one with about a 4 RE apogee. And our instrument, the retarding ion mass spectrometer, was on the higher one. So it was an interesting time in which the working group was trying to decide when we would run all the instruments, because we didn't have enough telemetry to run all of them all the time. And so there was sort of an arm wrestling going on between our group, where we wanted to measure down here at low latitudes so we could understand the plasmasphere, and then the people who wanted to measure the polar cap, the auroral people, who wanted to measure the polar cap. And of course we compromised, and to our chagrin, we had to measure the low energy plasma all the way around. Well, that turned out to be a great gift, because what we found was when the spacecraft Dynamics Explorer was up in over the polar regions, there was huge amounts of ion outflow. The polar wind, the polar cusp was all seen up there, and it changed our perspective. So what we asked was, and this is like the mid 80s, we said, well, there appears to be a whole lot of ion outflow, and that was looking from RIMS and then from the Lockheed instrument at higher energies, the energetic ion composition spectrometer. There was large amounts of plasma flowing out of the polar cap. So we ask ourselves, is there enough outflow so that if you sort of guesstimate where things go, that it would give you the densities in the regions in the magnetosphere that we've already measured at higher energy? And the answer to that was yes, it does, that there was enough outflow that goes through the lobes, although back then it was invisible. We couldn't see it in the lobes. We could see it on the RIMS instrument down low, but still IC, all the spacecraft that were out here measured nothing in the lobes. And so we said it must be invisible in the lobes because of spacecraft potential, but there's enough of it to make the plasma sheet, and there's enough of it to make the ring current. So that got us started thinking about the ionosphere as a source. Now, I want to get you to think about the magnetosphere in a slightly different way. We think about it in terms of the different regions of plasma that are there. We think about the lobes, we think about the plasma sheet, the ring current, now the warm plasma cloak, the plasmasphere, the radiation belts. We're thinking about regions of plasma. And the magnetosphere is created not by just superimposing these regions, but it's like a tapestry. So you've seen tapestries hanging in the wonderful palaces of Europe and around the world. Tapestries are made by a series of threads of different colors that are woven into this tapestry to create the images that you see. And so I want you to think about the magnetosphere as a tapestry, which is that it's created, these different regions that we see are created by the motion of the ions and electrons that are flowing through the magnetosphere, that are being energized by the cross-tail potentials, by wave particle interactions, things like that, and that create these regions. But that a single ion can start in the ionosphere as a polar wind ion of a few eV and flow into the polar cap. It picks up some energy a little bit in the lobes, up to maybe 10 eV, up to 100 possibly. And then when it goes into so it's been a 1 eV and then tens of eV. And then when it goes into the plasma sheet, by process that we'll talk about, it's energized to keV, the energy you see in the plasma sheet. And as it drifts in, it's energized further by the betatron acceleration to make the ring current, which we see. And then some of it, lower energy, makes the warm plasma cloak. So this is a tapestry. And what we've got to try to measure is the motion of all the ions and electrons which create this, and then whose presence actually contributes substantially to the reconnection that takes place in the plasma sheet. So it's difficult to understand the magnetosphere. It's important, but it's difficult to understand the magnetosphere just from the point of view of moments and composition ratios. I mean, those are valuable, like the ratio of H plus to HE double plus is valuable as an indicator of the solar wind. or He plus and O plus to O plus. These ratios are valuable, but they are difficult to explain when you measure them. And the other thing I just want to mention is that magnetic activity, the level of magnetic activity is important. It helps us know what's going on in the magnetosphere, but the magnetic activity from the currents in the ionosphere and the ring current and those kinds of things are more a result of what the magnetosphere has done, the solar wind and the magnetosphere. They're more of a result than a cause, although we correlate with them because they tell us that the magnetosphere is in a different state. So I'll talk some more about that. So there are two types of particles that flow out of the ionosphere. I've named them after the people who largely discovered them. One is I call strange wave particles. Strange wave particles are based on a papers that Bob Strangeway has done using fast data. Strange wave particles are particles that require energy input from the magnetosphere in order to heat the ions enough that they flow out. And that's typically the polar cusp and the night side auroral zone. Those are strange wave particles, and they're moving up into the magnetosphere. They do vary certainly with the solar wind and what's going on in the southward component of the solar wind. The other particles are Banks and Holzer particles, and that's named after Peter Banks and Tom Holzer, whose theoretical work, together with Ian Axford and later Bob Schunk, showed that the top of the ionosphere should be sending off a flow of polar wind all the time, even with no energy input other than the sunlight causing or creating the F region. And then on the top of the F region, there would be a charge separation electric field set up that would accelerate the minor ions off the top of the ionosphere, H plus and He plus principally. They fill up the plasmasphere, but then at higher latitudes, they move out into the lobes. So these two types of particles, the strange wave particles, which require energy, particle energy, wave energy, that sort of thing, to get out of the ionosphere, and they can be higher energies, and the polar wind, which flows all the time from any time the ionosphere is in the sun, you're going to create polar wind and it'll flow off the top. And these are very large fluxes. The polar wind flux is of the order of 3 times 10 to the 8th ions per square centimeter per second, or 10 to the 25th to 10 to the 26th ions per second flowing out of the ionosphere into the lobes and into the inner magnetosphere. It's a substantial contributor. The strange wave particles are also substantial contributors, mostly O plus, H plus, He plus, but from the auroral zone. So they're more limited in the area that they are sent out. And here's some images of those. These are strange wave particles. These are from work by Lynn Kistler's group. This is outflowing oxygen. The sun is off to the left in each one of these pictures. This is basically where the cluster spacecraft was out to about 20 RE, sampling particles that were coming out of the polar cusp. And there's dawn side passes, center and dusk side, and then non-storm time, storm, main phase, and recovery. And over here is the occurrence frequency, and you see that red is 100%, yellow 75%, and on down. But in the center of the tail, there's very high probability that you're going to see polar cusp outflowing particles in the lobes of the tail. Those are the strange wave particles, and they come out of the night side auroral zone as well. Now, the polar wind, and this is a more elaborate version schematic of the polar wind done by Bob Schunk, but the polar wind is coming out of the ionosphere anywhere the sun is shining on it. At lower L shells, it fills up the plasmasphere, and at higher L shells above, say, 6, it's going to flow up into the polar caps, and the convection field is going to carry it across the polar cap and out into the tail. So the sun is over here, here's the polar cusp. And a lot of those particles go through regions like the polar cusp or the night side auroral zone in some cases where they get further energized. But there's also a standard thing that energizes the polar wind continuously. This is an ion trajectory that was done by Matthew Huddleston in his PhD thesis looking at polar data, the thermal ion dynamics experiment data on polar, and modeling the trajectories. Work on this was also done by Jim Horowitz and several others, John Cladis. And it shows that as an ion leaves the ionosphere, so sun's to the left, on the day side, this is a polar wind ion moving out at a few eV. And as it follows the magnetic field lines, and as it moves up into the magnetosphere, it goes through an area where the field line is curved. And when it's curved, it causes a drift, a curvature drift on the particle, which in this case is out of the page. And that drift moves the particle across the crosstail potential and energizes it. So few EV becomes 10 EV or so, and then it flows out through the lobes. Now here are times: 2 hours, 3 hours, 4 hours, about 5 hours by the time it gets to the plasma sheet out here. But it's in the lobes, it's very low energy, less than 100 EV, tens of EV. And then when it reaches the midplane of the magnetosphere, there's very distended magnetic field lines, and it has a very large curvature drift, again, out of the page, drifts in the direction of the crosstail potential and gets further energized. And I'm going to come back and talk about that. But that just shows you that a polar wind particle can become more energized in the lobe and then further energized as we get on into the midplane. Now, to dramatically show that prior to missions like Polar, we could not see what was going on in the lobes. We developed our ideas about how the magnetosphere works, not being able to see anything in the lobes. And so naturally we began, and the fact that there was H plus in the solar wind and H plus in the plasma sheet, it about the same energies, it seemed natural that the solar wind was the source of the plasma sheet. Because when we flew through the lobes, there was nothing there. It turned out there was a lot there, but it was low energy enough that we couldn't see it. This is an orbit of the Polar spacecraft looking at the low energy ions. This is 1 EV to 400 EV, and this is the spin angle up here with the magnetic field, two magnetic field directions and the RAM velocity. We had, knowing that we couldn't see anything in the lobes unless we could control the spacecraft potential, we were able to add the plasma source instrument, which put out an ion electron plasma so the spacecraft could draw back to it the charge that it needed to stay at plasma potential. The photoelectrons leaving the surface of the spacecraft typically charge it positively, and so you have to put electrons out there that the spacecraft can draw back. So up here in the top shows you that's the instrument, and there's the PSI. That's the spacecraft potential control device, which is turned off until right here it turns on. And all of a sudden, instead of seeing nothing, you see the polar wind flowing along the magnetic field line out of the northern hemisphere. And we're looking at energies here now of 1 to 10 EV, whereas before the neutralizer turned on, there was nothing to see except a few particles that were up in the 100 EV range. So it's out there, the lobes are full, and the lobes are full all of the time, as long as the ionosphere is in the sunlight at the feet of those field lines. So that's an important thing. On the cluster mission, they had spacecraft potential control, and they had a very clever complement of instruments that could measure the wake direction of the plasma that was flowing by the spacecraft when it was in the lobe. And you could tell by the by the characteristics of the wake, the direction that the ions were flowing and what their energies were and their fluxes. And it turns out the lobe was full of polar wind and some polar cusp particles as well. The polar wind particles, the fluxes were what were predicted by the theory almost 20 years before. This is just shows you for the cluster spacecraft. And again, these are the scale here is 100% occurrence frequency, 100% red all the way down to 0 in blue. This is, look, the sun is to the right. This is cluster going through the lobes and the plasma sheet here. And you can see the red, a lot of red, yellow, showing that along those orbits, the lobe has polar wind flowing out. That's looking from the side. If you look down from the top, you see the red parts of orbits are in the center part of the tail. And if you look from the behind the Earth toward the sun, you can see that in the center part of the tail is where the flowing polar wind is. So it's there and it's important and it's filling the lobes almost all of the time. Now this is from Stain Holland and the group that worked on the cluster mission, looking at where the outflowing polar wind goes as a function of the BZ, the IMF BZ and the solar wind. So when the BZ is southward, you get a convection electric field, a crosstail potential, and that causes the outflowing polar wind to be pushed into the center part of the tail. So this is BZ positive, where there is only a small, if at all, convection electric field, and the polar wind comes out of the polar cap and vents out of the tail. And Stain was able to show that 90% of the polar wind goes out of it exhausts out of the tail. A small amount of it may get caught up way down the tail, but positive BZ, it vents out, we don't see it. But as soon as the solar wind turns BZ southward, then there's a crosstail potential and a convection field that starts to drive the polar wind into the plasma sheet region. And the higher that southward BZ is, the closer in these ions come in. And he's able to estimate that 90% of the ions that are flowing down the tail and flowing out the back of the tail in positive BZ conditions come into the plasma sheet and then are affecting the region in which reconnection takes place. Okay, I want to talk to you about timing now. Timing. The purpose of this is to try to get an idea of how the solar wind plasma is contributing to the plasma sheet versus the ionosphere. We can do these proxy measurements of H plus over HE double plus, but remember, we don't know for the H plus part of that, we don't know where that came from, because solar wind H plus looks exactly like ionospheric H plus from a measurement point of view. This is a code written by Dominic Delcourt for his PhD thesis back in the late 80s. And Matthew Huddleston used it as a way of interpreting what we were seeing in the TIDE instrument on the Polar spacecraft. So I want you to look at some of these times. This uses a Sigonenko magnetic field and a Weimer convection field. This case is for a KP of 2. And he starts a particle on the day side up above the ionosphere, but using fluxes. Later, he uses fluxes that are measured bipolar down low. And you can see the timing on here. The timing, these are 10-minute marks as we go through. And so it says that from the time it leaves the ionosphere out to about here is an hour and a half, 90 minutes. And for the next 30 minutes, it moves into the plasma sheet region and gets energized and is moving toward what becomes the ring current. So this is looking at the magnetosphere from the side, and looking at the motion of an ion that started at 10 eV and ends up with ring current energies. Looking down from the top, here it is starting on the day side, goes into the dusk sector, and then moves in, becomes the ring current. And here's looking from the tail, and here's the energy. So it starts with 10 eV, slightly above polar wind. And for that first hour and a half, it increases up to a few tens of eV. When it goes into the plasma sheet region, that's this part right here, it gains a kilovolt. And that's, again, from the curvature drift in the crosstail field, gives it a kilovolt. And then as it drifts inward, it's further betatron accelerated until it becomes ring current energies at 10 kilovolts. So I want you to look at the timing. It's about an hour and a half to 2 hours to get out here to 50 RE. The timing from the tail, from the lobe into the plasma sheet region is only tens of minutes. So if the lobe is full and if the BZ of the solar wind goes southward, these particles are going to go into the plasma sheet within 10 to 20 minutes. And we'll come back and say, how long does it take a solar wind particle to get into that region? Okay, so, and this same ion makes the polar wind, the lobal wind, the plasma sheet, and the ring current. Same ion moving through the magnetosphere. And of course, there are lots and lots of ions doing that. Okay, let's see. Now, people have expressed concern about just using an ion trajectory because they say, well, you know, your magnetosphere model is not self-consistent. You're not letting the currents flow and change the magnetic field and configuration and strength and all of that. And that's true. However, Alex Glosser has done a model, and this was published just this past year. It's a merged ionosphere magnetosphere multi-fluid model. So he feeds in polar wind. He's got a plasmasphere, a ring current, a plasma sheet, and it's multi-fluid. And he chooses a separate fluid for the ionospheric H+ and the solar wind H+. So this model can tell you the difference in where these H+ ions came from. And since that's the dominant ion, that's a really important thing. I'm going to show you something more about that in just a minute. This is a single ion trajectory that is very similar to the one I just showed you from Matthew Huddleston. Ion start, and the sun is off to the right here. The ion flows out of the ionosphere at a few eV through the lobe. By the time it gets here, it's about 100 eV, and it changes to yellow. It very quickly becomes 1 keV, and then as it flows back in toward the Earth, it gets to the red, it's 10 keV. So polar wind, lobal wind, plasma sheet, ring current. This is with a full MHD treatment, and it's giving a trajectory which is very similar to what we saw before. Now, in contrast to that, this is some very nice work by Sarathia, the group that's doing now, John Lyon, and the group that's doing a lot of trajectory modeling of storms and the magnetosphere. This is a paper published just a couple of years ago in which he starts ions at the bow shock and he lets them flow in toward the magnetosphere, and he follows trajectory wise where do they go and how long does it take. And this is with a northward BZ. And one of the things that was mentioned was that it is in northward BZ times in the solar wind that you expect Kelvin-Helmholtz instabilities to be stronger. This also has some reconnection in it, but of course with a northward BZ, it's not full reconnection, but partial, just because of a magnetic field orientation of the solar wind. But look at the timing. For a particle to get from the bow shock to the flanks of the plasma sheet, not into it, but out on the flank, it's 30 minutes. This is an hour and a half to begin to have some penetration toward the center. These are solar wind H+, some penetration toward the center. And this is 2.5 hours before the particles that started out here at the bow shock begin to get toward the center of the plasma sheet in the 2030 RE region. So in contrast, coming out of the lobes, the ions coming out of the lobes can get into the, because they're there very close, they can get into the plasma sheet in 10 to 20 minutes. Whereas for particles that come from the solar wind, it can be up to 2.5 hours. So the ionosphere is in a favorable position because it's close in the lobes. Okay, now this is Alex's results, and I just want to show you that hemispheres make a difference. Both lobes aren't filled all the time, but it depends on, of course, the season of the year, what part of the ionosphere is seeing most of the sun. But this is an indication of the relative contribution of the ionospheric plasma with the solar wind in the magnetosphere. This is ionospheric H+. This is ionospheric O+. This is solar wind H+. And the yellow means there's a lot of it, 100%. Blue means there's not much of it at all. So here's this is now in a storm, isolated storm. This is a period of 24 hours. This first set is in the growth phase of it. This is in the expansion phase. And then this is in the recovery phase. So what do we see in terms of what's contributing? In the growth phase, we've got a lot of, this is ionospheric H+, a lot in this lobe because it's favorably positioned with respect to the sun, and some in the both coming out of both hemispheres, but dominantly up to 100% in the lobe is ionosphere. This is ionospheric O+, and it comes out of the polar cusp and the auroral zone, principally polar cusp, and it's making about 50% of what's there. And then this is solar wind. So solar wind at the beginning of this has some penetration on the day side. Look back here in the tail region, in the plasma sheet region, 20, 30 RE, 40 RE, there's almost no solar wind. It's almost 100%. The plasma sheet back here is almost 100% ionospheric H+, plus ionospheric O+. Here's at the more in the expansion phase of the storm, still see the ionospheric H+ filling in, the O+, ionospheric O+. Still, the solar wind is not dramatically accessing the inner plasma sheet inside of 30 RE. And then in the recovery phase, the solar polar wind still flowing out, but it's starting to vent out the tail now. And the O+ is there, but diminishing. And the solar wind H+ is beginning to penetrate. And he shows that in the peak of this storm, the ring current is dominated by the H+ from the ionosphere plus the O+ from the ionosphere, with some minor contribution in the ring current of the H+ that comes from the solar wind. Okay, this is a way of showing, another way of showing what Alex's model does. Alex can tell the difference between the two H+ sources. So it's a tremendously important thing right now. This is something that Matthew Huddleston did using polar, measuring down low and measuring what's coming out of the ionosphere in different, this is noon, dawn, dusk, and latitudes down to 60 degrees, 90 to 60. These are different pitch angles. He measures in these different segments the pitch angle, the energy of the outflowing polar wind. Then he does an ion trajectory and connects that to the tail, each one of these, and sums them up. And he just shows back here a region that captures all of the portions of these trajectories where the energy has increased to greater than half a keV, up to 5 keV. So you start with a polar wind, you connect it with the trajectory, and you get this sort of an image or region picture from the side, and here's from the top. Looks a lot like a plasma sheet. And if you sum all of the outflow of polar wind and polar cusp, the energy, the densities that you get back here. The energies are a plasma sheet, and they are also the densities that you see. I just want to show one more thing, which is that it matters where the ion leaves the ionosphere, and then what happens in the solar wind BZ as that ion moves out of the ionosphere and into the tail. Because where it ends up in the tail determines how it's going to be energized. And so for ions, polar wind, that start when there's not, they flow across the polar cap and they don't have enough energy to get way back in the tail. They come into the tail more toward dawn and closer in. Those ions, because those field ions are not as distended, they don't have the curvature drift along with the cross tail potential, and they don't get energized as much, and they go around the dawn side and make the warm plasma cloak, which, as I mentioned earlier, can affect reconnection here at the nose. For those that flow farther, come from other parts of the ionosphere and flow farther down the tail, they're getting into the distended region where they're going to pick up a KeV or so when they come from the lobe into the midplane. And then as they drift in, they're going to come up to tens of KeV, like I showed in that other example. So it matters where the ion leaves the ionosphere and then what the solar wind BZ does as it's flowing down the tail, whether it vents out of the tail or where it comes into the tail. Okay, I want to show you a couple of examples of how MMS data can help us with this, because what we're talking about is trying to understand what has been called the plasma sheet boundary layer. So on the north and south side of the plasma sheet, the characteristics of the plasma and the plasma sheet are different in the closer to the midplane than they are at the edges. And we've tried to explain that in terms of sort of different ways the solar wind access can happen. But what it really is, I believe, is this plasma sheet boundary layer is showing you the transition of the lobal outflow plasma to the plasma sheet plasma. So very quickly, here's an MMS orbit. This is XY plane. It's coming into it's around the midnight sector. And here's the orbit, it's 24 hours. And these are places where the spacecraft, the plasma sheet thins and the spacecraft is in the plasma sheet, and then it thins and the spacecraft's in the lobe. And then it thickens back up, it's in the plasma sheet again, and then in the lobe. And so these are places where it's transitioning from plasma sheet to lobe to plasma sheet to lobe to plasma sheet. And we're going to look at this one in a little more detail. What you can see here is that when you go into the lobe, the energy drops from 1 to 10 keV down to about 10 to 100 EV. So these are lobal winds. And so now to show you what I'm talking about there, here's the XZ plane in the night side. And here's an example where the plasma sheet thins. This is sort of the projected magnetospheric shape. Plasma sheet thins and the spacecraft, instead of being in the plasma sheet, is in the lobes. And then Narutoshi Kitamura has looked at this particular case and did a nice expansion. So here's that one area that starts at 1900. This is a focused in now. So here's the plasma sheet part, here's the lobe part, back into the plasma sheet part. Those are electrons, here are the ions. And what you notice is that the energies again are dropping. This is FPI, the ions are 1 to 10 keV, drops down to about 10. It has spacecraft potential control. It's not a plasma neutralizer, but it's an ion emitter, and then out the other side. Narutoshi also took the low energy part of the FPI data, 1 to 300 EV, and did a pitch angle distribution. And so in the lobe, what you see is the particles are at 180 degrees. They're coming out of the northern hemisphere and flowing through the lobe into the plasma sheet. And in the plasma sheet part, you still see particles low energy. These are 0 to 300, but they're spread over 180 down to 90. they're picking up perpendicular energy as they come into the plasma sheet region. Here's HPCA data. H plus is in both the plasma sheet and the lobes. Here's HE double plus, which is in the plasma sheet part, but not in the lobes. And then oxygen's here, and HE plus. Both of those are flowing in the lobes. They're all the way across. So there's a lot to be studied here that can be very valuable for us. Okay, the last section is just to show you, to talk about how is it that the ionosphere can drive substorms and storms in combination with the solar wind BZ. This is a study done by Dan Welling, in which he does an MHD magnetosphere and he doesn't have a specific outflow, but he lets the magnetospheric part draw in what it needs in order to make all the equations work, basically. This is a southward BZ, where the whole, all the way back to 40 RE is dominantly ionosphere. That's the blue part. And then red is the solar wind. Looking down from the top, you see the ionosphere filling the center part of the tail. And then this is northward IMF, in which there is penetration by the solar wind, the red part, into the magnetosphere. Tom Moore also did trajectories that gave similar results to this. Now here's the substorm. Let's think about what happens in a storm. Let's start with a northward BZ. So the solar wind has been accessing with H plus and HE double plus into the magnetotail on the flanks. The time from the bow shock in is about 2.5 hours. The polar wind and polar cusp outflows, as the blue lines show, there's no convection field, there's no cross-tail potential, at least not very much, and they flow out of the tail of the magnetosphere. They don't affect the plasma sheet. Then the solar wind shifts to southward BZ, and the H plus and HE plus are still there because they came in earlier and populated. But the enhanced convection field drives the polar wind, instead of it flowing out the tail, it drives it into the plasma sheet. And the stronger the southward BZ, the closer in it comes. And once it comes into the plasma sheet, it gets energized. And looking at those trajectories earlier, we know that these ion trajectories can get you from the lobe into the plasma sheet in a matter of 10 to 20 minutes. And the energization can take place in less than 10 minutes once the particle is into the distended part. So enhanced convection drives polar wind and polar cusp into the center of the plasma sheet in tens of minutes. The ionospheric ions are energized by the curvature drift and the cross-tail potential. We've got mass loading and energization that distend the central tail magnetic field, setting up reconnection. And the large fluxes of polar wind and polar cusp ions, once they're energized, dominate the plasma sheet and the ring current and the warm plasma cloak. It's a different way of thinking about a substorm or a storm. The solar wind BZ is still the trigger, but the particles are delivered by the ionosphere through the lobes dominantly. So here's the process. Northward BZ fills the lobes, but it's flowing out of the back of the tail. The growth phase is when BZ turns southward, and these flows are put into the mid plane where they're energized and they stretch the tail. The distended tail increases the curvature drift and the cross-tail potential and energizes the ions. And then when it's loaded, reconnection begins in the expansion phase. That's being studied, all the reconnection part being studied by MMS in a lot of really nice detail. Starts the aurora, starts the ionospheric currents flowing, gives you the magnetic signatures in the auroral zone, those sorts of things. And then the nearly energized plasma sheet flows earthward and is further energized. The ring current strengthens so that both polar wind H plus and polar cusp O plus are dominant in it over the solar wind. And this large storm can develop and continue as long as the southward BZ is there, because the ionosphere is sending out polar wind continuously. And as long as the BZ delivers that to the midplane, the storm is going to continue. When BZ goes back to positive again, then the lobal wind begins to exhaust out the back of the tail and the storm stops. So in summary, what do we want to do? We need to try to understand how the ions and the electrons are even tougher than the ions, obviously, but to measure accurately at very low energies. But how the ions actually move through and are energized and make these regions, and how changes in BZ can cause a storm there. And our next steps need to be to run these merged models multi-fluid that can separate the solar wind H plus from the ionospheric H plus. There's going to be a lot of wonderful information that comes out of running these multi-fluid models. And we use those models to help as a roadmap to help understand what we're looking at in the particles. And we can include other multi-fluid ions, of course, solar wind, we can add He double plus, and then all the ions that you see coming out of the top of the ionosphere, particularly O plus, He plus, N plus, O double plus, some NO plus. And then the merged models using those and the particle tracing will help us understand what we're looking at with the particle measurements. And it also will help us understand how the environment for reconnection is created in the plasma sheet and at the magnetopause. We need to fly instruments that can focus on low energy plasma that have spacecraft potential control. This is really important. We don't always do this, and we need to get back to doing that on future missions. And we really need a mission that can comprehensively measure the outflow of ions from the ionosphere, all energies. There was one proposed to do this sort of thing in the last call for mission proposals, but it wasn't selected. It's really important to know the details of what the ionosphere is putting out. This is a summary, which I won't go through because but it's basically what we talked about. I wanted to dedicate this talk to Don Carpenter at Stanford and Ed Shelley at Lockheed, both of whom unfortunately aren't with us anymore, but I had the privilege of working with Don when I went to Lockheed in Palo Alto and study the plasmasphere together with the guy who Carpenter's knee is named after, for the first person to see ionospheric plasma in the magnetosphere. And Ed Shelley, of course, whom I enjoyed very much working with, who showed us that you can see O plus in the magnetosphere that has KeV energies. It obviously came from the ionosphere because there wasn't any other place for it to come from, and got energized. We have been, to a certain degree, not completely following through on what Ed showed us, because people now know that O plus is from the ionosphere, and they often talk about O plus as the reason that we know the ionosphere is putting particles out there. But remember, the ionosphere is putting a lot of H plus out there too. We just can't tell it apart from the solar wind. So there's some references that I have for you to consider that underpin all of the rest of the talk. And Jason, if I might, I'd just like to say thanks to my thesis advisor, Brian O'Brien at Rice, who is no longer with us. Martin Walt, who was the man who enabled me to come to Lockheed as a green PhD and gave me the opportunity to do work in these different areas, and working with Dick Johnson, Dick Sharp, and Ed Shelley, and Jerry Sharp and Kent Harris. That was the time period in which I also was able to meet Andy Nagy and Peter Banks and begin working with them, and they taught me an awful lot about the ionosphere. And then we later worked with Bill Hansen and John Hoffman, George Carrington at Michigan, Bill and John at UTD to build the RIMS instrument, and with Jean-Jacques Bertelier and Dave Young, and then Obi Stone, Stan Fields at Marshall, who built the TIDE instrument. So thanks to all of them for making my exploration journey possible. And I'm happy to answer questions.
Thank you, Rick. That was a nice presentation and a very nice overview. So let's move on to the questions. The first question is from Legion. Okay, Legion wants to know if this is, I guess it was from one of your earlier slides. I guess it was slide 3 or something where you showed one of the earlier pictures of the magnetosphere.
Yeah.
Yeah, so Legion wants to know if the green represents, this one, this slide. So if the green represents the polar wind, why is it not present in the cusp?
So in this one, and this is just a schematic, in this one, this is polar wind, and then the polar cusp is sort of indicated by this. Now, in one of the other pictures, the polar cusp, there's the solar wind axis that bounces out and makes the mantle. It's way out at the edge. The polar cusp, depending on the strength of the convection field, can be pulled in pretty low because the oxygen for a given energy, the oxygen has a lower velocity than the H plus would have. So it's sort of indicating that the cold H plus is flowing farther out, and the heavier ions that come out of the polar cusp can come in closer, can come across the polar cap and get directly into the ring current.
Okay. Legion also wants to know what measurements indicate no polar wind in the cusp.
So there is polar wind in the cusp. Polar wind that leaves the ionosphere outside of the plasmasphere, let's say on the day side, the convection field will carry it across, it'll come up out of the ionosphere, the convection field will carry it through the polar cusp on its way out into the lobe. So there will be an intermixture of polar wind and polar cusp on the day side. And then as it comes across the polar cap, they separate depending on their velocities, because the convection field drives them into the midplane of the tail at different places depending on their outward flow velocity.
Okay. So the next question is from Sergey Apetenko. Sergey wants to know that the parallel electric field was mentioned as important initial mechanism for an ion to leave the ionosphere. So can we believe this electric field exists all the time and does not depend on solar wind BZ? And what are the regions where this electric field exists?
Yeah, so so the way it works, and I have to wave my hands here, but the way it works is that in the F region of the ionosphere, which is dominantly O plus, but also has H plus and He plus, on the top of the F region, the top of the F layer, the electrons float a little bit higher in altitude than the ions, just because of their thermal energies. They float a little higher, and it sets up, it's called a charge separation electric field. And that charge separation electric field, which is upward, accelerates the minor ions out of the F region. So the F region is dominantly O plus. It doesn't accelerate the O plus, but the O plus electron charge separation accelerates the H plus and the He plus. So that's what you see in the polar wind. The O plus stays from a polar wind point of view, the O plus doesn't come out of the ionosphere, but it requires more energy. So the O plus can come out of places where energy is brought from outside down into the ionosphere, like in the polar cusp, where you've got solar wind particles that are bent in and that precipitate, that heat the ionosphere and heat the oxygen enough to come up out of the ionosphere. Same way on the night side auroral zone. So polar wind flows any place there's sun on the atmosphere, unless the flux tube above it is completely filled up, as is the case in the inner plasmasphere, where those flux tubes get full enough that you get a back pressure from up above and the polar wind shuts down. But any place from the outer plasmasphere all the way to the polar cap. If it's in the sun, you're going to get the polar wind flowing out.
Okay, thank you. Okay, so we move on to the next question. Yeah, Patricia Reef wants to know that, okay, this is, I guess it's something to do with the substorm slides which you showed on the link.
Yeah.
So yeah, in this scenario, the BZ turns northward at the end of the storm. But isolated substorms, the expansion phase appears to happen at a northward turning, at least at times. So how does this fit into the scenario?
Okay, so I'm not quite sure I understood, but let me just go through that again. Northward BZ, the polar wind is flowing, but it's flowing out the back of the tail. It's not being carried into the plasma sheet region. It's flowing, but we know that we can get H plus from the solar wind and some HE plus through Kelvin-Helmholtz instabilities on the flanks. So before the storm begins, one would expect to see H plus and HE double plus in the mid-plane region of the tail that has come in by Kelvin-Helmholtz instabilities or some possible reconnection. When the BZ of the solar wind goes southward, that's when the polar wind that's flowing out of the tail is very quickly pushed into the center midplane of the tail, tens of minutes. It's full. The lobes are full right up to the edge of the plasma sheet. And when the BZ goes south, the polar wind is pushed into the plasma sheet in large quantities, as well as some polar cusp particles. And that's what begins to load the tail, as opposed to the solar wind. The solar wind BZ is making this happen, but the particles are being delivered by the ionosphere. It's polar wind and polar cusp, pushed into the plasma sheet very quickly, energized very quickly, 10 minutes, and all of a sudden you've got a very different plasma sheet to set up reconnection. And some of the discussions we've had in the FPI working group just have to do with, we want to understand the reconnection process in detail, and MMS is doing really a great job in giving us that data. But we also need to know how the reconnection region is created and how it varies as a result of loading from the ionosphere and the lobes into the plasma sheet. Now at the end, so you load it, it distends the magnetic field, you get reconnection, the aurora brightens up, all the currents flow, you've got a substorm. If the BZ stays southward, it'll keep on pouring more ionospheric plasma in. That process will continue until the BZ goes northward, and then the polar wind that's in the lobes will no longer be pushed into the plasma sheet, but will flow out of the tail.
Okay. I assume that's what your question was, Patricia. If not, you can just hop in and speak if you want.
Oh, well, no. Yeah, Rick, I was actually talking about what's triggering the expansion phase. That occasionally a northward turning appears to trigger the expansion phase. And I was just wondering what room does that have in this scenario?
Good question, Pat. So what I think what we'd be talking about there is that the loading of the tail sets up the opportunities for reconnection. There's just more energetic plasma in the center part of the plasma sheet, and it's distending the magnetic fields. But in terms of when reconnection happens, what this scenario shows you how the plasma sheet gets loaded up and gets ready for reconnection. But then the reconnection itself is more, that's the reconnection part of the process and less of what I'm talking about. Am I making sense in what I'm saying? So this process that we look at sets up the plasma sheet, loaded with plasma, stretched magnetic fields, the kinds of things that you would expect would give you reconnection. But when it actually triggers the reconnection, that's the reconnection process taking place in this new environment that's been set up.
Okay, so okay, thank you. So we move on to the next question now. The next question is from Gianluca. Gian wants to know, since you have primarily focused on cold ions, Gian was wondering if you could add some comments to cold electrons.
That's the comment I made. Thank you, Gianluca. That the comment I made during the talk is that it is not going to be very enlightening, but it is very, as we know, because we've been talking about it, very difficult to do the cold electrons. You've got to try to figure out how to control spacecraft potential so that they get to you. And then you've got to be able to separate them from the photoelectrons that are coming off the spacecraft. And in changing environments, like in moving from the lobe to the plasma sheet, it's just very difficult. And I'm not an electron person in terms of instrumentation, but I know it's a very difficult thing, but a very important thing to try to do. The ions, at least, you can do trajectories for the ions, and then you sort of say the electrons are along for the ride. They're going to maintain charge neutrality, and you want to know that, and you want to know how they are affected by waves that come through. You want to know they are so important in the process, but very, very important, needs to be done, very difficult to do.
Okay. So, okay, the next question is, okay, you have mentioned that we had, the next question is from Bob Manka. You have mentioned that we hadn't realized the contribution to the lobes. So how much does the ionospheric plasma increase the density in the lobes?
The density in the lobes, and this was the problem about why we couldn't see it for so long. The density in the lobes is typically 1/10 of an ion per cubic centimeter. The plasmasphere densities, are 100 out to like 10. So if we measure down in the plasmasphere, we can see everything, or just about everything, until we get out of the plasmasphere into the trough. But the lobes are very low density, so it doesn't take much photoelectric current coming off the spacecraft to charge it up positively. And that's why you have to carry your own plasma neutralizer with you, or at least try to bias your ion measurement probe versus the spacecraft. Try to bias it negatively so you can draw in some ions. So that's what the lobes are tough, because the density is very small, and it's small enough that photoelectrons can make the spacecraft charge easily.
Okay.
I hope that answers that for you, Bob.
Yeah, Bob.
Yes. Thanks, Rick. I just didn't quite understand compared to what we used to density in the lobes. When you account for the ionospheric plasma, how much does it increase it?
So, good question. It obviously increases it, but I don't have that number. That's a great question. It doesn't, you can tell, Bob, from the polar measurements there in the lobe, the polar wind was flowing, blowing and going there, and the spacecraft was still charged up in the tens of volts. So the polar wind was flowing in the lobe. The spacecraft was there in the middle of it, but couldn't see it. So that would suggest to me that the increase in density in the lobe there would be increase in density, but not enough to make a difference with respect to spacecraft charging.
Thanks, Rick. Very nice talk.
Thank you.
Okay, so we move on to the next question. Next question is by Vishwajit Ojha. Vishwajit wants to know if there is any effect on the negative ions in the ionosphere in these processes.
On the negative ions, that is something that I've never thought about. It's a great question, but I guess I don't really have a comment on that.
Okay. Okay. Okay, so next question is from Nick. Nick wants to know what mission or orbits or number of satellites you envision to measure the ionospheric outflow. What type of measurements?
So the idea would be to try to get as broad a coverage as you can of what's flowing out of the ionosphere globally. And so you'd want to be, you can be down low, you want to be up above the F region, because you want to see polar wind, which is coming out of the F region. You want to see the effects of like the strange wave particles, the particles that are energized by precipitating electrons and protons in the auroral zone, by solar wind precipitation in the polar cusp. You'd want to measure all of those. So you need a full energy range of less than an EV with good geometric factors all the way up into the auroral energies, and do that in as many places as you can. So multiple spacecraft to maybe altitudes of a couple of thousand kilometers with ground-based support to do the lower parts of the ionosphere, and do that all the time, so that then when we do run these multi-fluid merged ionosphere, magnetosphere models, we can use, and we're looking at an event, we can use the measurements from low altitude of what's coming out of the ionosphere, and then model what we expect to see in the magnetosphere from the trajectories, and then compare it with what we see. So as good a coverage as you can get down above the ionosphere, but fairly close, multiple spacecraft if possible. And as I mentioned, the MEMEX mission that was proposed earlier was that sort of mission. And we just will need to do that.
Okay. Okay. Thank you. One more question from Antonova Elisabetta. Antonova wants to know, what do you think about the role of auroral ionic distribution in magnetospheric filling?
So I didn't hear that. So the auroral zone ions, what was the right after that?
Conic distribution.
Conics, okay, yeah. So that's absolutely a contributor. Interestingly, in sort of a secondary way, if you think about that storm scenario, you're doing polar wind out of the ionosphere, you're doing polar cusp. The BZ goes southward. The lobe particles are pushed into the plasma sheet. They are energized and reconnection begins. And those particles, reconnection then causes precipitation. Particles are accelerated down into the atmosphere, the auroral zones on the night side. And then you're going to get backscattered electrons. You're going to have parallel electric fields that accelerate the ions in the auroral arc regions. You're going to have lower energy ones, and many of those particles will go back up into the plasma sheet, although several of those particles will not go back up into the plasma sheet, but will go into the opposite hemisphere. It just depends on the pitch angle that they leave the ionosphere with as to whether they go back out into the tail or whether they just go to the conjugate hemisphere and precipitate. But conics then would come into play through the interaction of waves that are around on up the field line with the particles that are leaving the ionosphere, either because they are backscattered or they have gone through an electric field, or their pitch angles have been changed. And you would expect those particles to make a contribution to the plasma sheet or the ring current, depending on where they come up out of the ionosphere.
Okay, thank you, Rick. I guess we have a couple of questions with Jason. Jason, would you mind to?
Yes. Yeah, certainly. There was one more question here actually from Dave. And Rick, I'll just take this opportunity to mention all the comments. There have just been many compliments about your talk, great talk, excellent talk. And Dave also echoes that. Very nice, well-constructed story, he says. And then also, yeah, so Dave's question was, just this final question here. What role in populating the plasma sheet do head start ionospheric ions play, perhaps in terms of timing? And by head start, he means ions that get accelerated, for example, by wave particle energization below about 1,000 kilometers in altitude.
So would they be auroral zone type ions? I mean, where do you, head start is a term I'm not familiar with. What areas do they come from? Are they global, or are they focused into coming from the cusp or the auroral zone, or because that would be an important element of where they go and how they make a difference.
Yeah, and feel free, Dave, if you want to chime in. Yeah.
Yeah, Rick, Dave Klumpar.
Yes, good to hear from you.
So in part, the previous question about ion conics is what I had in mind. But let me just add that, the ISIS observations, which I'm very familiar with.
Yeah.
We saw the ion conic distributions we measured them at 1,400 kilometers, and they had energies in excess of hundreds of eV. And we saw them in the cusp. We didn't see them really in the polar cap itself on the open field lines, but on closed field lines at pretty much all local times. That's what I was referring to. I just coined that term head start off the cuff.
And so let's see. So the conics, I guess, are going to be caused by ion cyclotron waves or something that adds perpendicular energy to an outflowing ion.
Yeah, that's the conventional story.
Okay, and so in terms of the sequence of things, you would think that the BZ southward tells the ions in the lobe to move into the midplane and make it more set up for reconnection to happen. Then reconnection happens, and as Pat pointed out, that can sometimes be in a northward BZ, but the midplane is loaded mass-wise, and these particles are getting energized, so it's ready for something to happen. And then once the reconnection happens, then you would start to put particles precipitating into the ionosphere, which could set up parallel fields and do that sort of things, and then send ions outward in an environment with a lot of wave activity. So that would say that the head start ions might be a result of the buildup of plasma in the tail, as opposed to happening ahead of it.
Interesting.
In terms of that scenario, at least, that I was talking about.
Yeah, that's I'm not aware of a study that's actually tried to determine the prevalence of conics as a function of magnetical time, but more importantly, as a function of substorm timing.
There was
interesting study.
Yeah, there was some ion conic work that Chris Olson did when he was at Marshall using the Dynamics Explorer data. I think maybe the polar data, but I think it was Dynamics Explorer. He found them near the equator along a dipolar field line. But there's certainly a lot of conics, and I know y'all have measured a lot of that and have a great data set on it. They're bound to be ions that have been accelerated in a direction perpendicular to the magnetic field somehow.
Yeah. Thanks, Rick. Great story. Great talk.
Thank you.
Yeah, certainly. Just echoing that, great story, and certainly a hearty thanks again, Rick, for this presentation. And got some great questions here, and this, of course, it was recorded and it'll be on our YouTube channel in case there's some content just we might all want to review and process and think about this some more.
Right.
And so, yeah. So with that, next week, of course, we'll have on our schedule Dr. Sasha Zhu from University of Michigan talking about the multi-scale ionospheric response during geomagnetic storms. And then also, as Rick mentioned, in 2 weeks from now, on the 8th, we'll have Alex Glosser presenting some more about those multi-fluid models and the general question of magnetosphere, ionosphere coupling. So with that, it concludes our session for today. And thanks one more time for our speaker, Dr. Rick Chappell, and see you guys next week.
Thank you, Jason. I enjoyed being with everybody. Thank you.
Certainly. Very welcome. Thank you.
Have a great week, everyone.
Yep. Bye, everyone.
Bye.